So hopefully you've tried some on your own and checked the solutions, and if you've got any questions, text me. I'm going to do a few more with you and then let you finish up the section by yourself. This is the 2007, and this is a non-calculator one. So if you will follow along in your notebook, this is talking about the volume of a hot air balloon expanding, and the radius of the balloon in feet is modeled by this function, R of t, and t is measured in minutes. So it says the graph of R is concave down. The table shows selected values of the first derivative of the rate of change of the radius of the balloon over the interval. And the radius of the balloon is 30 feet when t equals 5. And it gives you the volume of the sphere formula. So part A says estimate the radius of the balloon when t equals 5.4 using tangent line approximation at t equals 5. Is your estimate greater than or less than the value? And give a reason. Okay, so if you look at part A, tangent line is y equal mx plus b, so we need a slope and we need an ordered pair. So at t equals 5, we have an ordered pair because it says the radius is 30 feet when t equals 5. So that's our ordered pair, 530. We get our slope because this is the first derivative here, so we go to 5 and our slope is 2. So we plug in 30 to 5, solve for b. B is 20. We write y equal 2x plus 20. We plug in 5.4 and we get 30.8. So 30.8 feet is the radius for part A. So and it asks whether it was a greater than or less than. It said the curve is concave down, so that means that your tangent line is sitting on top. So that means it's greater than the actual value. All right, part B, it says find the rate of change of the volume of the balloon with respect to time when t equals 5, indicate units. Now this is related rates. Remember we did that a long time ago, so we're going to use this formula. So we're going to do dv of dt, and I'm going to do just my power rule of derivatives, so you're going to get 4 pi r squared dr dt. And we're just going to plug in 4 pi 30 for our radius, and 2 for our dr dt, because that's our slope or our derivative, our rate of change. And if you plug all that in, you get 7,200 pi feet cube per minute. Now remember, volume will always be in cube, and you're talking about feet and minutes. So part C says use a right-Riemann sum with 5 subintervals indicated by the data in the table to approximate 0 to 12 of r prime t, and use correct units, explain the meaning. So we're going to do a right-Riemann sum, and remember again, you're going to use the width being your x value, the difference in the x values, and we're going to use the right point. So if you have, first one you've got 2 times 4, the next one you got 3 times 2, second one you got 2 times 1.2, 4 times 0.6, and 1 times 0.5. And if you add all that up, you get 19.3 feet. And part D says here's your approximation greater than or less than the actual one. And since it's a decreasing function, if you look up there, it's an under approximation because you're using right intervals. And the explanation for what it is the change in radius in feet from 0 to 12 minutes. So this is the 2006 one. Again, this is a non-calculator one, and it's talking about a rocket, And the chart gives you t in seconds and velocity in feet per second. And it's going from 0 to 80. And part A says find the average acceleration of rocket A over the time interval 0 to 80, indicate units. So remember, acceleration is the derivative of velocity, so you're just going to use your slope formula because they said average, so that's average rate of change. So you're going to do v of 80 minus v of 0, 80 over 0, and if you work all that out, you get 11 over 20 or 0.55 feet per second squared. So you got feet per second divided by seconds, so that's why it's second squared. Now, part B says explain the meaning of the integral of 10 to 70 of v of t in terms of the rocket's flight. Use a midpoint Riemann sum with 3 subintervals of equal length. Now, notice you're only going from 10 to 70. So when you're doing your subintervals and it wanted you to do 3, so the difference of that is 60, so they're going to be 20 wide. So your first one's going to go from 10 to 30, your next one's going to go from 30 to 50, your last one 50 to 70. So midpoint will just be the value in between your two endpoints of your interval. So when you do the midpoint, it's equal width, so you got 20, and then you're doing f of 20 because that's the midpoint, which is 22, plus f of 40, which is 35, and f of 60, which is 44. And if you add all that up, you get 2,020 feet. And that's the distance in feet that the rocket traveled from 10 to 70 seconds. So part C says rocket B is launched upward with an acceleration, and they give you that formula. At t equals 0 seconds, the initial height of the rocket is 0 feet, and the initial velocity is 2 feet per second. Which of the two rockets is traveling faster at t equal 80 seconds? So we know the velocity of rocket A is 49. We need to get the velocity of rocket B, but we have acceleration. So we are going to integrate. So you've got 3 over the square root of t plus 1, so you're going to use u substitution. And so when you do that, I'm going to pull the 3 out. I got u raised to the negative 1/2. I'm going to use my power rule, and I end up getting 6u to the 1/2 plus c. So if I plug my u in, I get 6 square root of t plus 1 plus c equal v. So I'm going to plug 2 in for v, plug 0 in for t, and solve for c, and I get c to be negative 4. So I can go back, and now I can write my velocity function for rocket B. So it's v equals 6 square root of t plus 1 minus 4. And so now I plug 80 in, and I get 50 feet. So rocket B is traveling faster. 50 is greater than the 49 on rocket A. So our next one in your notebook is the 2006 Form B. It's a non-calculator. You see you've got a chart of time, velocity, and acceleration, and you're talking about a car traveling on a straight track. And so part A says using appropriate units, explain the meaning of the integral from 30 to 60 absolute value of v of t, approximate using a trapezoid approximation with 3 subintervals. So you're only going from 30 to 60. So when you look up at your table, you're going here. So you go from 30 to 35, 35 to 50, and 50 to 60. So those are going to be your subintervals. So you're going to come down here, and you're going to do 1/2, bring your 1/2 out. And remember, this is absolute value of velocity. So my first width is 5, absolute value of negative 14 plus negative 10. My second width is 15, absolute value of negative 10 plus 0. plus 10, absolute value of 10 plus 0. And when I put that all together, I get 185 feet. Now, what is that? That's the distance it traveled from 30 to 60 seconds. Now, part B says, using appropriate units, explain the meaning of 0 to 30 of A of t dt, and find the exact value of that. So when you come in here, you know that's the change in velocity in feet per second from 0 to 30. So 0 to 30 of A of t is the same thing of 0 to 30 of the first derivative of V of t. And remember, when we take an integral of the derivative, we just do V of 30 minus V of 0. So we can pull that from our table, negative 14 minus negative 20, and we get 6 feet per second. So part C says, for 0 to 60, must there be a t when V of t equal negative 5? Justify your answer. So you're going to use intermediate value theorem. And what that theorem says is, if you have a function continuous on an interval AB, and W is a number between f of A and f of B, then there is at least one value C between A and B such that W will equal f of C. So if I take the values 35 and 50 from the chart, and let's let W represent the negative 5, they're saying, is there a t when V of t equals negative 5? Then by intermediate value theorem, it says there is, because V of 35 is negative 10, V of 50 is 0. So negative 5 falls between those two. So intermediate value theorem says there must be a time between 35 and 50 that equals negative 5. Now part D says, for 0 less than t less than 60, must there be a time when A of t equals 0? Justify your answer. We can let the mean value theorem prove that, because that says a function's continuous on an interval of AB and differentiable. Then there's one number C in that interval such that the derivative of C is equal to the average rate of change. So if I use the value 0, 25 in the chart, V of 25 minus V of 0 over 25 minus 0 does equal 0. So that means there must be a time between 0 and 25 such that the V of t, the derivative, equals 0, and A of t is the derivative of velocity. So that proves part D.